Welcome everybody. Our speaker this afternoon is Dr. Afşar Saranlı from the Department of Electrical and Electronics Engineering. Afşar Saranlı received BS degree from Middle East Technical University, MS from Imperial College London, and PhD from Metro again. He worked for Photon Dynamics company in Canada between 2000 and 2004, and then he joined to academic staff in Metro as an assistant professor. Currently, he is an associate professor in electrical engineering department. His research interests include leg autonomous mobile robotics, sensor-based state estimation, robot vision and pattern recognition, development, simulation and modeling of control systems, stochastic and adaptive image and signal processing, and related subjects. He has 4 international patents and several publications in these areas. Thank you very much for joining us.
Thank you.
I hope you will all enjoy the talk.
Good afternoon, everyone. I would also like to have an idea about what's the composition among you. Can I see who is from the Faculty of Engineering, first of all? Okay. Faculty of Architecture? Okay. Faculty of Education? Is there any? So, Faculty of Architecture, what is the distribution? Like architects? Architecture, internal design, or not internal design, but industrial design? City and regional planning. Okay, very good. Arts and Science, Faculty of Arts and Sciences. Okay, very good. And from engineering, electrical engineers. All right. So, mechanical engineers. Civil engineers, other engineering, which are your branches? Biomedical engineer. Sorry? Geological engineer, you guys?
Petroleum and natural gas.
Which one?
Petroleum and
okay, very good, very good. So very, very diverse group of people. That's very nice. Now, my name is Afşar. I've been essentially a teaching staff in METÜ since 2005. So let me, this photograph is actually quite old now, but for some reason I couldn't really manage to get all the people together again to update this picture. In fact, one of my Master of Science students over there on the right hand side, he's right now about to start in our department as a teaching staff, as an assistant professor, so I'm kind of feeling weird, feeling all the years passing by, first time, it's like the first time one of my students is starting as an instructor in METÜ, so I guess, I still feel young though, so I will, start my talk like this. I'm going to talk about who am I, where I come from, then I will talk about who we are as a research group. Then I'm going to talk about what do we study. And then I'm going to a bit touch on the particulars. And I want to talk about what do we want to do in the future. Okay? So obviously I'm not going to go too much into the details of what we do, but rather we'll try to give you an idea about how our research field is composed. All right? Okay, so if you have any questions at any point, feel free to ask. Although Gülbin Hoca has really summarized, I really, I graduated in '93 from the electrical engineering department. Then was a rather intense, 1-year Master of Science study in England, and then I came back for my PhD here. It was in the field of control systems, but the thesis topic was more on the signal processing and pattern recognition side, okay, for those of you who are familiar with those areas. Then I really wanted to have some time in industry, so we went not to the university, but to industry in Canada. So I spent about 5 years there. The field I worked on was the inspection of LCD, TFT LCD panels for very large TVs. It was including image processing, some signal processing and instrumentation control. That means, the control of very large inspection systems. And so since 2005, almost 11 years now, I've been around here as a teacher in Metro. Okay. So I also want you guys to remember where you are. Okay. I personally feel quite privileged to be in Metro because I have seen a lot of schools, I have seen a lot of places, but our campus, our teaching environment, our research environment is really something that's not everywhere. Okay, it may or may not be the best, whatever, but essentially, as a whole package, let's say, this university is something to be proud of. So one thing that I want you guys to remember is where you are, okay? Provided that you put the effort in this university, I feel and I strongly believe that you can do anything you want because you have the resources, you have the people, and you are here as well. So I guess we have everything to be able to achieve great things. But obviously, sometimes especially we are near our families, we feel a bit relaxed. We don't want to work that hard. The same students, when they go to abroad, they work much harder than they would work here. So please remember that, okay? So I feel that, we are in an excellent ecosystem of students, teachers, and the general working environment. All right, so now who we are is that we essentially is a combination of two laboratories right now. One of the laboratories is called ROLAB. It's part of the electrical engineering department. It is essentially the robotics and autonomous systems laboratory. This is a laboratory that me and my students are mostly occupying. And recently, or maybe more recently, we have also established an interdisciplinary laboratory called Atlas. It is located in the Moksinmer building. Maybe you have seen this building in the campus. It's a pretty colorful building. The difference of that laboratory is that it is a combination of mechanical engineering, computer engineering, and electrical engineering teaching staff, research staff being part of collaborating on the field of robotics. Okay? So, what do we study? Well, we study what we call dynamically dexterous legged robot locomotion. So, what is this? I mean, it is robotics, all right, but it is legged robotics, and it's more than that. It's one particular way of doing legged robotics. Now, let me show you a video to a little bit inspire you guys. Okay. So this is the video of the fastest athlete right now. Maybe it has changed. Did it change? Usain Bolt is right now the fastest athlete on earth. Okay, and this is a slow motion video of him running. Okay. Now, when you talk about legged robotics, traditionally, okay, legged robots are pretty static. Okay, people design robots to basically move, one leg at a time, and there are huge legs. So robots stand on each leg while trying to balance themselves on that leg and trying to move the other leg to a new position. Okay, so if you look at Japan's most successful robots, the Honda robot, for example, you would see that it's basically very inefficient. Okay. There are large batteries, the motion is not very smooth, the balance is really shaky, although it's becoming much better. The main idea there is that you try to keep your stability, and then when required, okay, when you want to change your feet, you are basically disturbing your equilibrium for a temporary period and then becoming stable on the other foot. Okay? But if you look at humans and if you look at animals in nature, I'm going to show you another example. You can see how energy efficient it is. That's one thing. Okay? So it is very smooth. There is very little motion in the body center of mass. There is very little contact with the ground. Most of the time the system is just flying. Okay? Just for very brief amounts of time, you can see that there is energy transfer to the system so that the flight essentially is continued. Okay? This kind of efficient motion, probably you guys also felt it when you are walking very efficiently. You don't feel very much vibration. You don't feel an inefficiency of energy. Okay? So it's a very powerful way we as human and animals, as we will see, are moving around. Okay? So our basic idea is that robotics is not only about creating robots that resemble humans. Okay? We are in fact inspired by nature in the sense that locomotion, being able to move, is a very basic survival skill, and this is a survival skill that robots will need to have in the future. If we want the robots to be able to go, at places that machines today, cars, trucks cannot go. Okay, we know that most of the surface of the earth are inaccessible to any man-made vehicles right now. But we can see that animals and humans can actually go at places that nothing else can go. Okay? Now this is another interesting video that I find very inspiring. Okay? Okay, so it's a bit dark, but let me maybe maximize this. Okay, so this is again a slow motion video of the fastest running animal on earth, which is the cheetah. Okay, so you can see, we can observe a couple of things here. One thing is the same, right? The animal basically is in flight for most of the time. So it's a legged animal, but it's as if the animal is flying for a large percentage of the time. Okay? Legs have a certain pattern of touching the ground, and for very small durations of time. And there is another interesting thing, which is look at the head of the animal. As we know, animals and humans, most of our sensors are carried in the head. Okay, our eyes, our inner ear, which is our gyroscopes and accelerometers, feeling the gravity and our motion, right? Even our olfactory sensors, right? Our noses are on our heads. Okay? So one interesting thing here is that while this animal is running very fast, the head is really so stationary. Nothing is happening with the head. It's like as if it's on the wings. Okay? So the vision of this animal, right? What the animal sees is a very clear picture of what's happening around it. Okay? So we are inspired by this because if we want to really build machines that can very successfully move around on Earth, we have to really look at solutions from nature that are giving us ideas about how this is happening. Okay? So one key concept here is the stability concept. Okay? Stability means this animal does not fall. This animal does not, hit somewhere. This animal is dynamically stable. So what we call dynamically stable. So this kind of motion is what we are interested in, and we call this dynamically dexterous locomotion. Okay? So this is essentially our research area. Obviously, you can see, for example, if this animal is hunting something, okay, this is some kind of a target that the cameramans are pulling so as to film the animal. Okay, but you can see how the gaze of the animal, right? Nothing is shaking, nothing is vibrating. The animal is locked on the target. So we feel that, you know, if we want, for example, our robots to be able to see in the future, we will need this kind of a stable locomotion so that the vision sensor, the cameras, are actually acquiring images that are very clear and which do not have distortions that's going to affect our image processing algorithms. Okay. Now, is it the only kind of motion that we see in the nature? No. There are other dynamic kind of motions which require more of a planning rather than a very, you know, flight dominant motion. Let me show you, you know, how another kind of animals are using their capabilities to locomote. Now, these are not the fastest animals on Earth, but these animals are the kind of creatures that can go where nobody else can go. Okay? These are mountain goats. They can climb, you know, incredible places, and even places that humans can't climb. I mean, humans, as you know, are very resilient, and they are very competitive in terms of climbing. They can pretty much go anywhere, okay? But these animals are actually living there, okay? So they since birth, you know, these animals are, it's like their natural playground, okay? Very sharp cliffs where there are tiny, you know, places to put their food. They can just play and hunt and go anywhere, okay? Now this is also very inspiring because here there is more of a planning type motion. These animals, sometimes they are very careful. They decide on where to put their feet. You know, they can run, but sometimes they can climb carefully, and they can go anywhere, almost anywhere on Earth. Okay? All right. So what's happening in the robotics world? Okay? Now, these are the inspirations of the kind of robotics research that we are interested in. And this kind of research is not entirely new. In fact, it started in the 1980s. Okay? This is a clip from the Discovery Channel. And what I'm going to show you is very old. Okay? This is from the MIT's leg laboratory. Okay? So I'm going to blow this out for you. Now, these robots were created in the 1980s, where computers were very slow. You know, actuators were not that powerful. But still, you know, the key research was there. And the person that was doing this research was called Mark Rybert. He's the founder of the Boston Dynamics company. Have you heard about the Boston Dynamics company? Their videos are everywhere, and I'm going to show you a couple of them. But there is a reason why these guys, you know, this guy in particular is so successful, because he has been studying this problem since 1980s, where nobody believed that these things can do anything useful. Okay? So these videos, as you see, they are very shaky because they are very old. Okay? But you can see that all the foundations of what Boston Dynamics is doing right now was there. Okay? And it was only a couple of years back, maybe, you know, three years ago or something, that the guy was saying that, you know, I am for the first time seeing the light and the end of the tunnel. Okay? So why? Because this guy was committed to legged robots, but the world was not ready, in the sense that nobody actually thought that this is really gonna be successful in nature. But in reality, it did. And maybe some of you guys know that Boston Dynamics is bought right now by Google, and we don't know what's going to happen. Okay? But most likely, this technology will be spreading to civilian applications as well, rather than the defense application that was the focus a couple of years back. Okay? So this is the early work in legged robots, and although there are many theoretical problems that are not solved yet, pragmatically there was a lot of useful results that led to quite successful systems. Any questions up to this point? All right. Okay. So, let me also show you guys what is the state of the art. This is again coming from maybe the earliest towards the latest. Some of these you might have already seen because they have been around for a while now. This was called the Big Dog. Okay, this was a large four-legged robot that was supposed to carry a lot of weight. Okay, so this robot has hydraulic actuators, so very powerful leg actuators, and there was a gasoline engine on it. We don't have sound here, but there is a constantly running gasoline engine on it, which is driving the hydraulic pumps. So it's a very noisy kind of robot. Okay, but you can see that this is very successful, and the success is in the fact that there is dynamic control algorithms running in the background, which are driving the leg. So what is being done is that the animals, or not the animal, but the robot's body motions are measured, and the algorithms actually create the control signals for the legs, so that the legs try to stabilize the angle of the body so as to prevent falling or tripping over and so on. And some of these experiments are very impressive. For example, this happened to be on ice. So in ice, obviously friction is very low, so the legs are going everywhere. But you can see how the algorithms are fighting to keep the equilibrium of that robot. We know from the past, since the space program, that control algorithms can be very powerful. Our passenger planes are flying with control algorithms. The rockets, space rockets are flying by control algorithms. So we know that control algorithms can actually be very fast in responding to different scenarios and different situations, okay? But this is the first application, first very successful application in the outdoor, outside the lab environment. Somewhat later, these guys developed this further, and they came out with this robot. Now, this is called Wildcat, again from the same company. Mind you, this is not a regular company. This company has almost 200 PhDs in their R&D department. So it's like larger than maybe 2 or 3 departments combined. Okay, so this is a purely research-oriented company. Okay, now what is new here is that the running is now getting into play. Okay, not only the system is trying to balance itself, but it's trying to apply certain gaits, what we call running gaits. So the legs start to touch the ground in a certain pattern, and this pattern, together with those control algorithms, are creating some kind of what we call a limit cycle. A limit cycle is not a stationary point, but it's an oscillation around a stationary line. So this thing is not falling, it is stable, but it's not static. Okay? It is essentially a stable limit cycle. So there is oscillations in the body, but these oscillations do not diverge, and the robot doesn't fall, and so on. Okay, so there is a behavior which can be maintained, like the running or walking is such a pattern essentially. Okay, you can see that there is now turning motion, and very very impressive running skills. There are also other lab-grade trials. For example, this one was a trial to achieve the fastest possible running on a four-legged robot. Okay, they basically accelerate a running pad underneath, and you can see that the robot is actually connected from its middle to some pivot point here. So there is no lateral motion. Okay. The robot is not allowed to fall to the side. So it's a planar motion. Okay? The robot can only move forward or backward, and can have tilt, but cannot fall to the side. Okay? So these guys have achieved quite an impressive running speed. Okay? Almost like 28.5 miles per hour. So this comes to about 50 kilometers an hour. Okay? It's like a car on a road, basically. Okay? But you can see that as the speed increases, at some point, there is not enough capability of the algorithms to keep the balance, so the robot becomes unstable. Okay? The latest in this series of research is a bipedal robot. Okay? This one is known Atlas. You know, somewhat coincides with our lab name, and that has an impact on the Google scores that we have, obviously, because when you write Atlas, obviously you end up with this rather than our lab. But anyway, this is a biped, so it applies all the same principles, but this time on a two-legged robot. And obviously, you know, the arms have some weights right now, and it is similar to the way we use our arms, okay? We also use our arms to maintain our balance, okay? Now this is very impressive because the way this machine walks is way different than the way Japanese robots walk, okay? So if you, I mean, we are, I think, very close to a point where you can dress this thing, and if you look at the legs and the way this thing walks, you will not be able to tell whether this is a human or a machine, okay, in terms of its walking efficiency, okay? So we are getting very close to achieving very successful types of robots in this area, right? Anyone with any questions at this point? All right. So what do we do? Okay. This is our area of research, but we are in particular interested in multi-legged robots. This includes bipedal robots, but we don't specifically work on bipedal robots. We are rather working on multi-legged animals, more or less inspired by insects. Okay. Now you might say this might be a bit, you know, disappointing for some people who wants to see the robots as, you know, intelligent creatures which resemble humans. Okay. But in reality, if you look at nature, there are many animals that have tremendous survival capability, but they don't have that much intelligence in the way we think of intelligence for humans. Okay? If you think about an insect, the insect can survive in a very different environments. This insect can go to a lot of places, so there is the capability of moving from one place to another, and for its survivability, it can achieve a great many tasks, okay, like feeding, like mating, and being able to find food, being able to bring food to its living place, and so on. So insects are very efficient animals that can survive in nature. So for us, this is also some kind of intelligence. Okay? I mean, if you leave a human being in an island, okay, and tell him to survive, maybe he can survive, maybe he can't. And if he can survive, you will basically think of this human as an intelligent one because he managed to find the ways of surviving in that environment. Okay? In that sense, many simpler animals also possess survival intelligence, what I call. Okay? So our specific projects are focused on building incarnations of insect-inspired robots. What is so good about the insect? What we think is that they are very robust. Okay? They are simple, they are efficient, they can achieve a great many things with quite a bit of simplicity. I mean, if you analyze an insect, its nervous system is very simple. Okay? Maybe a couple of hundred neurons. Okay? And then its organs are very simple. its legs are quite simple, but still, if you look at it, it can go anywhere with that capability. Okay? So for us, we want to build systems that are very simple, but which capture the essential part of being able to move in nature and being able to achieve certain given tasks. Okay? So our focus is on multi-legged, insect-inspired robots. Okay? And we started with a TÜBİTAK project maybe 7 or 8 years back. Okay? And we built a number of these robots. And these are not our ultimate goal. Okay? These robots are just research platforms for us in order to study interesting problems facing legged robots. Okay? Now, obviously, let me show you a couple of videos about how this particular robot looks like. Okay? These are videos from the termination of that project. It was presented as part of the final report of that project. So what we did was we basically put this robot together. It was obviously a tremendous experience for our students because first of all, they designed all parts of this robot. And they have seen that they can do this. They have also seen that they are able to bring such a complex system together and make it work. And we also managed to find out where we can find parts, which partners we can have some subsystems manufactured and so on. For example, the legs of this robot are composite springs that a company in Ankara have manufactured. Okay? So they managed to, put together a setup where they manufactured a number of those legs and delivered to us. Okay? Let me show you a couple of other videos from here. This is like, this is the backyard of our department. So there were some kind of a treed area there, some slopes and so on. So then we managed to test a lot of different cases here. Let me show you maybe. So when the robot is very simple, you can actually make it work in a much more interesting environment. Okay? If the robot is very fragile, it has a lot of actuators, then something may break, something may not be able to function in that environment. But when the robot is very simple, you can make it work in a much wider range of scenarios. These are a bit more or less the same. Let me show you. Okay, so this can, for example, this kind of locomotion, it can achieve quite impressive locomotion capability. It can cross over amorphously shaped obstacles without having specific planning. So this robot does not plan to put its feet into individual specific locations, but it has like in the insect world, its nervous system has a simple pattern generator that is driving the legs, but the resulting motion is quite stable. Okay? It can cross many different obstacles with almost the same type of leg pattern. Okay? It can climb stairs, although, if you design obviously an algorithm specific to stair climbing, you can achieve a much better performance. But even without anything specific, that means the same kind of central pattern generator type motion, it can still, fail from time to time, but recover and continue its motion. Okay. So this is more or less our research platform that we are still using to do research on. Okay? So what kind of problems we are interested in on this particular robot? Well, for example, one research piece was to analysis of the leg shape and its effect on the stability of the robot. Okay? So we have circularly shaped robots, and we have evidence in biomechanics that humans are also walking with some kind of a rolling motion on their feet. As you know, our feet is not flat. Okay, our feet is flexible and it's very small. So we are really being, when we are walking, we are rolling on our feet. Okay, so we wanted to see what is the kinematics. Kinematics means the geometry of motion when you have specific shapes of the system, as well as the dynamics. That means if these are not static legs, but they are springs that can flex, what is happening with the dynamics of the robot? What kind of algorithms we can design in order to improve the stability of the robot? Okay. While doing this, obviously, we also study one-legged models. Okay. Why? One-legged models are much simpler, but they can imitate the behavior of a multi-legged animal as well. Okay? So by studying one-legged models, we can develop algorithms that can also control multi-legged robots. Okay? So a lot of our research also uses simplified mathematical models in order to come up with control algorithms for more complex robots. One thing that I was particularly interested in the last couple of years was how to deal with the sensor data on legged animals or legged robots. Okay, you have seen the motivation of a head on an actual animal, which was very stable, and the sensors on it was acquiring very clear signals. Okay, so what we were studying was the effect of visual acquisition on a legged robot. As our legged robot moves, obviously the camera has undergoing certain oscillations, so the images are distorted. Okay, there is an effect called motion blur. If you have tried to take a picture when you are in motion and you haven't set the camera parameters properly, you will get a photograph which is kind of a smeared version of your actual scene. Okay, that's called motion blur, and it's an integral part of the data that we acquire if we are on a mobile legged platform. So we started studying how we can deal with this. Can we design a robot head that is similar to what we have in nature in order to use angular motions to compensate for the robot's motions so that we have a better acquisition of images? Or, after the images are acquired, there are mathematical models, mathematical methods to compensate for the distortion. In a sense, correct it to some extent. Okay? We were also interested in acoustic perception, and one of my students had a very nice Master of Science thesis out of that. It was related with exploiting the acoustic signals that are coming from the robot. As you know, if you're walking, you constantly generate some kind of acoustic signal. Your legs are touching the ground periodically, and there is certain signals being generated. So what we tried to do was we tried to exploit the acoustic signals that are coming from our robot, in particular the legs touching the ground, in order to identify the surface that we are walking on. Okay? Obviously, the sound that is coming from legs hitting this kind of a surface, for example, by just hitting this, I can tell that it is empty underneath. Okay? So that signal tells me a lot. And we managed to, classify about 10 different surfaces just by listening to the, naturally generated sounds of that robot. Okay? So this gives us an ability to use not only vision sensor or touch sensor, but also the hearing sensor in order to come up with some information about what kind of surface I'm walking on. Okay? Why this is important? Because the kind of algorithms that you would use, let's say, if you are running fast on concrete, might have different set of parameters than if you're running on, let's say, grass. Okay? So you may need to dynamically adjust some of your parameters depending on the surface that you are working on. Okay? my brother is with the computer engineering department. He was also interested in essentially decision making for locomotion. Okay, he was working on some kind of a variation of logic in order to make decisions about how the robot should move when the robot's dynamics is involved. So not for wheeled robots where you can make decisions statically, you can just stop and make a decision and continue. But in a legged robot, right, you have to make decisions with time constraints because you are constantly in motion. Okay? So logic does not apply because standard logic, if there are those of you who are interested in mathematical logic, logic is good for static decision making. Okay? So it's not that good for decision making under time and resource constraints like battery voltage, you have to make a decision in half a second and so on. So this research dealt with trying to extend logic in order to deal with dynamic systems. Okay, so let me try to summarize where we want to go from here. We have a couple of things in mind. There are others, obviously. But for now, we are interested in alternative approaches to stabilization of legged motion. Okay? What are those alternative approaches? Well, you have your legs, and you can try to control your legs, but you can also help yourself. Okay? If you look at, for example, the cheetah's video, there is a huge tail. Okay? The tail is moving around, and it's not moving around just like a passenger. It's moving around in order to help the animal balance itself. Okay? The tail has a certain mass, and its motion is not random. It's a motion that is helping the animal have a better efficiency of motion. So that is, for example, one alternative. We are also looking at more engineering approaches like a reaction wheel, which are used in satellites to change, the orientation of the satellite without touching anywhere and without air friction support. Okay? So we are looking at different ways we can help to balance our dynamic robots. Okay? So another way we continue to look at is, can we have better ways of placing the sensors? In particular, can we place the sensors on a stabilized platform? Can we achieve this stabilization more compactly in a more efficient manner such that critical sensors like vision, inertial sensors and other types of sensors can be placed not on the body of the robot, but on a platform where you get a better chance of acquiring good data. Okay? We are also interested in how we can process the noisy data that is coming from a variety of sensors. Okay? A very important set of sensors for robotic applications, flying, running, diving robots, okay, are inertial sensors. Inertial sensors are your gyroscopes, your accelerometers, sensors that are becoming much wider in your phones, in your different devices and so on. So processing the noisy data of these sensors in order to somehow navigate your robot is an interesting research area. And it has its roots in control theory. What we call estimation theory is the mathematics of being able to estimate certain variables based on the motion of the system as well as sensor data coming with noise. Okay? So this has its roots in probability theory and control theory that we are working on. Finally, I'm also interested in computer vision applications of legged robots. In particular, I'm interested in what happens if you bury these robots in realistic environments where the visual environment is very cluttered. Okay? So when you want to task your robot with doing something in a realistic environment, there is vegetation, there are a lot of visual clutter, there may be grass, there may be trees, and you might be trying to track an object, or you might be trying to detect something that is dangerous and so on. So processing images coming from such cluttered environments is a very interesting problem. So that's something else that I would like to look at in the coming years. Right. So that is pretty much all that I have planned to talk about. But I can answer any of your questions if you have some.
About energy source. As we are left animals, we carry our energy with us. But in case of robots, in most of the cases, there are cables that carry the energy.
Well, that's a very good question actually. Although not entirely true what you have said. For example, this robot that is illustrated, it carries its own energy on board. That is called power autonomous. And it's a very important concept, as you said, right? It is important that if you want your robots to be mobile, to be able to go places, achieve certain tasks, you need to carry your energy with you. And that requires solution of interesting problems in being able to manage the power, being able to conserve power. That means, one of the biggest problems of kinematic robots, like the ones that are carefully placing their, arms and legs at different positions, is that they have very powerful motors and they have very large gear ratios. They are very powerful, but they waste a huge amount of energy as friction inside those joints and gears. Okay? For example, the robot that we are working on has only one motor per leg, and the leg is just rotating. So there is no complex mechanics going on. It's just a leg rotating. So as you simplify the robot, your energy efficiency goes up. And also, as you limit the time you touch the ground, you also increase your energy efficiency. If you look at the athlete running, its contact with the ground is so limited, both in time and in space. So as you touch the ground in a much more limited way, you conserve your energy. And another way of conserving energy is through mechanical storage. Okay? And that brings us to the concept of a spring. As you know, a spring is like a wonderful device, because a spring, if you let's say impact the spring to some surface, what's going to happen is that the spring will compress. The energy that you are putting in will be stored mostly inside the spring, and if you can manage to recover that energy while, for example, you are jumping, most of that energy is given back to the system. So in biological animals, humans, animals, our legs do not only have muscles, they have also springs. Okay? The tissues that are connecting our muscles to our bones are actually stretching in order to store some of that energy and give it back as a kinetic energy back to the system. So yeah, that is very important concept, and one that is being targeted by this kind of dynamic legged robots. Okay? Yes?
What's the main driving force for the robotic research? The defense industry or civilian purpose?
That's also a very good question, I think, because obviously, in pretty much all countries, defense is the primary motivation for the governments to invest in this kind of technology. But for us, there are many motivations. It's not only defense that is, maybe defense is not the primary motivation that we have. For example, there are biomedical applications. These are, for example, protheses and ortheses. Let's say disabled people that cannot walk can be made to walk by externally supporting them with suitably controlled legged robots. Okay? Well, obviously, you know, if you're obviously animals may also need this kind of support, but humans, if they are disabled, obviously they cannot sustain themselves. So it's so important for them to recover their mobility. Okay, so there is good research applying these concepts either in prosthetics. Prosthetics means non-actuated prostheses, as well as ortheses. Ortheses are where you actually build robotic devices. Okay, for example, there is no muscle actuation, let's say, in the legs of the patient, and you build the robotic system and you attach it to the lower body, and you are able to bring the person up. And
like brain-machine interface?
Not really. I mean, the interfaces might be much simpler. For example, you know, there is work being done in trying to, for example, you can bring somebody who cannot walk up, but still use, you know, what is that called? Crutches. And you can use the signals in the crutches, maybe some buttons on the crutches to activate the lower robotic system. So we don't need brain-machine interfaces. Obviously, if we can do that, and that's a research in biology, maybe medicine and electronics, we can obviously move on to the domain of science fiction movies, right? Which are, I think, quite close at this point, right? So, biomedical motivations, pure scientific motivations, I mean, we are very curious people. We don't need any particular applications to be interested in engineering systems, but obviously defense applications are also. But why would Google buy, for example, Boston Dynamics? Boston Dynamics was funded by DARPA and American military, but right now it's being funded by Google. So it's going to be interesting to see what's going to come out of that. Okay? Any other questions? Yes?
You pretty much talked about control algorithms, so I understand that these devices need a very good controller, I mean CPU controller. What kind of controllers they are required, or are they ready-made, such as Arduino controller, or they are designed from a scratch?
Okay, so so there are different robotic devices, right? For example, this one, although on this system we have two general purpose PCs, but these are embedded PCs that are very compact, okay? So they have a different standard. They are basically screwed together. So we have two computers, interface cards, motor drivers, all is inside it. But you can do with simpler. Now, since we started building this, microprocessors have accelerated so much. There are single board computers that are much smaller, and they have the similar processing capability. But this robot is special in the sense that we don't need that much complex control algorithms. I mean, here, all we have is a central pattern generator. The pattern generator generates a periodic signal, which is transformed into the motion of each leg, okay? And then there are just motor controllers that are trying to follow that signal. So in terms of control, this is very simple, but the morphology of the robot is such that you put this robot on the ground, it just, you know, it goes and it overcomes obstacles and so on, and you don't need something special. But if you think about four-legged robots, like the ones from Boston Dynamics, then there are very, very powerful control algorithms constantly fighting, you know, to keep the balance of the robot, so you need much more powerful computers there. Okay? So it depends on the type of robot and the difficulty of the control problem. Other questions? Teşekkür ederim arkadaşlar.
Teşekkür ederiz. Bugünün anısına.
Çok teşekkür ediyorum. Çok sağ olun arkadaşlar dinlediğiniz için. Umarım ilginç bir akşamüstü olmuştur.